So here's the kind of porosity model that comes out of this NMR business to say, this is what we have. In fact, kind of Richard picked up on this on the very first slide, saying you've got a rock, let's break it out into its component parts of what we're working with. So when you read NMR publications, they show something like this. Especially for a sandstone, we have rock matrix, quartz, the clay. They partition it between dry clay and clay-bound water. So that's an aspect that we have. When we correct for shale on our porosity measurements, this is what we're trying to get rid of, that clay-bound water that's messing things up. Then over and beyond that, we have, okay, what is in our larger pores? Movable hydrocarbon, movable water. And finally what we have, capillary bound water. This is the water that's bound to the rock. So in other words, if you do a log analysis and they run a drill stem test or they perforate and they get no water, the water you're seeing then from the Archer calculations, that's the immobile part. Now, the thing with the NMR is it can actually partition then between the different pore sizes. In this case, we've got three to consider. The larger open pores between the grains. We've got the capillary bound water in the small pores that's not moving. And then finally, we have the clay bound water there. And what they do then, the basic process is they're using the giant magnets, as it were, to fundamentally tip those hydrogen nuclei. So as that picture shows, they're kind of little bar magnets, and they flip them over, and then they release them, and then they start to resonate, and they get back to their original position. And the time it takes kind of depends on where the hydrogen is. Is it in a big pore, or is it in a very small pore? So the documents I read said that if you have water in a bucket, and you do an NMR log on that bucket, it takes 3 seconds for those hydrogen to finally realign themselves with the magnetic field. If you're in a smaller pores, then it'll snap back faster. Clay bound, it'll snap back really quickly. So it's fundamentally a measure then of pore size. And so this is the kind of thing you would see for many sandstones. Here's our scale, relaxation time in milliseconds. That's thousands of a second, so 1,000 is 1 second. So my bucket of water response would be over here, I guess. Here's the movable water, and in fact also movable hydrocarbons in the bigger pores. Here's the capillary bound water, and finally here's the clay bound water out there. So that'd be the situation then if we're looking at a clastic sequence. Now, how they try to predict then permeability is to use the Timmer-Coates equation, or sometimes use the SDR equation, Schlumberger-Dole-Ridgefield. And the permeability is estimated as a function of porosity. The NMR tool actually measures porosity, and the partition between the free fluid and the bound fluid. Or this is a slightly souped up version taking the geometric average. So here we go, once again, they label it BVI, that is the bulk volume irreducible. That's what I would call BVWI, that's what I use for my log interpretation of what's going to move and what's not. They're measuring it. So for people who wrestle with producibility, it's saying, well, you've got the money, pony up, we'll find out by having actually measured by a logging tool. So permeability then will be one of the things that's predicted. It's not perfect. And the reason, well, one of the reasons it's not perfect is because we are measuring the distribution of pore sizes, pore body sizes. And what's actually controlling permeability are the size of the pore throats. So right now we're in a reservoir. It's called the Hilton Hotel. This is an enormous pore all in. But the permeability, getting things in and out of this room, is all based on that door right at the back. So that's what we'd really like to measure. But we're almost there by at least getting the distribution of pore body sizes. Okay, we'll look at an example from Kansas. It'll be a Chester sandstone sequence, Pennsylvania. The Trees Oil Company ran this. We're down in Haskell County. Okay, look at the conventional logs. Well, here's the bottom of that sandstone. There's a few limestones put in too. A little shale there. Then we're getting to shales up here at the top. We look at the porosity logs, neutron and density. both scaled then on limestone units, and so we say, aha, classic indication of quartz, in this case it's a sandstone. That's also verified by the photoelectric curve here, reading about 2. Well, that's close enough to 1.8. Fundamentally a sandstone there. Right at the top, notice this porosity drop down. This is kicking out, that looks like a thin limestone there. Then we get to the shale. Then we get to another sandstone up here. And then here we are, another kick over that says limestone right at the top. And then we go to shales. So we can read an awful lot of the geology directly from the conventional logging responses. Here are the resistivity measurements. Deep induction, medium induction, we've got some guard log there. Here is the shallow resistivity being affected by the mud filtrate. The medium and the deep are reading close together, so invasion doesn't seem to be a big issue. We can take that deep induction to be our RT. And as we move through the sequence, we see right at the top, underneath that limestone, we've got something that looks quite good. So there's something we'd focus on. Now we'll look at the MRI. And talk about too much information, it's just insane. They're showing you the same thing over and over again in different ways. But let's look over here. We've got, as usual, on track 1, we're going to see the gamma ray in green and the caliper dashed. And also we're going to see the porosity from the NMR broken out according to the relaxation times. Over here, we're going to see the permeability in red. We're actually going to see the spectrum of the relaxation times out there. We're going to have a clay line in green, and everything to the left of the clay line says that's clay-bound water. We have a BVI line, and that'll be then everything then to the right of that is going to be free water, and everything between those two is going to be bound. And finally, we're going to see a nice color presentation out here that's going to band up the gray is going to be capillary bound water, the water that's in the pores that won't move. Blue is going to be the free water, that if we perforate, we're going to get water coming in. Hydrocarbon in black could either be oil or gas. And then they put query gas because they're picking up then on the neutron density gas effect. And finally, there's green, MCBW. That green banding is going to be our clay-bound water. So here we are. So we see the gamma ray yet again. There's a shale down there, there's a shale there, there's a shale up there. Here's the permeability prediction then in the red, and that'll be scaled in millidarcies. And then you are seeing now the output in that, remember, everything, I think the green line is roughly here, everything to the left of that green is clay-bound water. Clay-bound water, clay-bound water, just where it should be according to the gamma ray, the shale. Then everything then, here's the other line, everything on this side then is in the open pores. This is between the sand grains and it's movable. And anything between, that's going to be the immobile. So shown in this presentation, kind of grand slam, we have, here's that lower sandstone part. The grey is not moving. The blue is movable. A little bit of oil and hydrocarbon right at the top of that sand. You could perforate down there. Maybe you'll get a little bit of oil and water. It might be residual. You're going to get a lot of water, no question. Then we go to the top. Right underneath that limestone at the top, we see this is a nice development here where you can see there's the immobile, there's the free, and actually they've written on the log where they perforated right there. They said we're going to perforate there because we expect either no or minimal water content because all the water here is bound. Here are the results of the test then, 5463 to 5495. So gas to surface 40 minutes, recovered 1889 feet gas coated oil, 300 feet gas coated oil and water, 500 feet of gas and oil cut water, 403 feet of gas cut water. So lots of oil, gas cut stuff, but lots of water. But look at this interval, 5463 to 5495. So we'll look at a close up. Whoops.